Hi there, it's Chem Coach Powers, and today we're going to be talking about reaction energy. We're starting chapter 16, and we are going to get going on 16.1. So this is the start of our thermochemistry unit, and today what we're going to be really focusing on is the first part of chapter 16.1. We'll get to the second part of that a little bit later. So this is kind of like a 16.1 part 1. So I want you to distinguish between heat and temperature today to convert between Celsius and Kelvin temperature scales. That should be reviewed for you, hopefully. To define specific heat, to calculate changes in energy using the specific heat equation, and then to explain some of the basic principles of calorimetry. So coming out of here today, you're going to tell me the difference between heat and temperature in terms of what the energy is like. You're going to be able to convert between Celsius and Kelvin and vice versa. You're going to be able to say, hey, if I give you specific heats of two substances, you'll be able to tell me which will change temperature more quickly. And if I give you any three variables in a specific heat equation, you'll be able to solve for the fourth. I'll give you three, I should say, for the fourth. All right, so when we think about thermochemistry, we already kind of know a little bit about thermochemistry. We talk about photosynthesis, for instance, or a match that's burning. And these can tell us a little bit about the reactions that are taking place in a system that are thermochemical equations, right, or thermochemical reactions. So basically, every chemical reaction, for the most part, is going to have some sort of change in energy, right? And these changes in energy are going to be like, I'm going to give off energy, or I'm going to absorb energy, right? So there's going to be either an absorption or a giving off of that energy. And so we kind of know those things as exothermic and endothermic, right? So if you absorb energy, then that's an endothermic reaction. And if you're giving off energy, it's exothermic. So thermochemistry is defined as a study of the transfer of energy as heat that accompanies chemical reactions and physical changes. So we're going to focus in on the heat part. Later on, we'll focus on some other things, but right now we want to think about heat. And we oftentimes call this enthalpy, all right? So if you hear that word enthalpy later on, you'll see, we'll define it. But that's sometimes kind of used interchangeably with this idea of heat, or enthalpy of a reaction, or heat of a reaction. So how does a thermometer know how hot the substance is? Like, what does that mean when a thermometer rises or falls? Well, remember, it's all about the kinetic molecular theory, right? It's about particles that are moving around really, really fast and causing an expansion, okay? So in that thermometer, those particles start moving faster, they expand, and they get further and further away from each other. And so that's going to tell you that something is getting warmer, or if they condense because something is absorbing their energy, then they're going to get smaller. So the thermometer is going to go down lower, right? So remember, again, that this is all about the transfer of energy. It's about kinetic molecular theory. And temperature is a measure of the average kinetic energy of a system, right? And so we're really just looking at the measurement of the motion of the particles, right? So temperature is the measure of the average kinetic energy, or the motion of the particles, the average motion of the particles that are in that substance, right? And remember that this was one of our assumptions for the KMT, that temperature was the average kinetic energy of the particles in a substance. But remember, temperature is not the same thing as heat, okay? A little bit of review here. Remember that that's the average kinetic energy of the particles, and we measure that in degrees Celsius or Kelvin for temperature. But when we're dealing with heat, we're dealing with something entirely different, okay? We're dealing with something that has to do with joules, right? And we're talking about the total amount of heat energy in a system when we're talking about heat. So here is our formula to convert from Celsius to Kelvin. Kelvin is equal to 273.15 plus the degrees Celsius. So you should just use that formula if you want to convert from Celsius to Kelvin. Just add 273. And if you want to go the other way around, you want to go from Kelvin to Celsius, you just subtract 273. If you're wondering, like, how do I figure that out? Remember, the absolute zero Kelvin is the coldest temperature you get, right? And so you can say, well, what would Celsius be? It's got to be below zero, because it's 0 Celsius is freezing, so it must be negative 273. So 0 Kelvin equals negative 273.15 Celsius. So that's kind of a way that you could think about that formula. Remember that the higher temperature means more movement. The faster something is moving, the more collisions it's going to have, the more energy it imparts, and so you're going to have a higher temperature. Okay. Think about this property. Is it extensive or intensive? Remember that those definitions mean intensive is something that is not going to change with the amount of matter, but extensive does. Well, temperature does not change with the amount of matter. I could have a little bit of, water, and I could have a big, huge pool of water, and I could have the same temperature on those. And so temperature is an intensive property. However, the heat is extensive. Heat does depend upon the amount of matter. If I have heat energy, a pool is going to have a whole lot more heat energy than a little tiny bit of water, right? So look at these two pieces of metal that are separated out, right? So if we look at 30 degrees Celsius here for that whole piece of metal, well, each of those by itself, is also 30 degrees Celsius, right? So they have the same average kinetic energy. And that's kind of the way we want to think about that. It's an average. All right, so absolute zero. You guys remember that? Absolute zero is the temperature at which the lowest amount of particle movement is present, okay? Now, we used to say that there was zero particle movement, that all matter stops moving at that point, but we do still see there's residual vibrations that still take place sometimes at absolute zero. On the quantum level, you can't cease everything. So absolute zero is the lowest temperature at which basically matter is basically, sorry, I'm not helping you out here very much. It's the temperature at which the particle motion is at the lowest point possible. Okay, does that make sense? So think about very minimal particle motion. Now, if you wanted to convert these, it would be quick and easy, right? If I want to see what Celsius is in Kelvin, then I just have to add that 273. And if I wanted to go the other way for those bottom two, and I wanted to look at Kelvin to Celsius, then I have to subtract 273. Okay. All right. So those values, if you guys had a chance to pause and practice that, are there right now. All right. So again, heat transfer of energy between samples of matter due to a difference in their temperatures. Okay. So this is due to the difference in their temperatures. You will always have heat energy transfer from objects that have higher temperature to objects that have lower temperature. Think of heat as a verb. It's the transfer of energy, right? So when I talk about the amount of heat, I can think about heat being moving. Heat is moving from one thing to another, right? And if I talk about heat energy, then I can think about it more as a noun. So heat energy, I could think a little bit more as a noun, but heat is the actual transfer of that energy. Remember that heat is always traveling from objects of higher temperature to objects of lower temperature. And remember, our units for heat are expressed in joules, capital J. All right, so which way will heat flow when these two metal blocks are placed next to each other? You got a 50 degrees Celsius block and a 20 degrees Celsius block. So think about it, right? Heat always transfers from the higher temperature energy object to the lower temperature object. So it's going to be going from the 50 degrees Celsius to the 20 degrees Celsius block, okay? All right, so we want to think of three things with regard to the amount of heat energy that can transfer from one object to the next. First, the mass. The amount of mass an object has is going to increase the total amount of heat energy it has, right? So you can have more heat energy transferring from objects that have larger mass. You also, so in this case, the 5,000 grams can transfer more heat than the 50 grams, right? If they're at the same temperature. You also have to think about the size of the temperature change. All right, am I moving 1 degree or am I moving 100 degrees? Because a 100-degree change in temperature is going to be much more significant than a 1-degree change, right? And so you have to think about the size of the temperature change. And then the nature of the material is another one you have to think about. Metal, for instance, is really good at transferring heat energy. Water is not. Water will hold on to energy. It takes a while to heat water up, but then once it's heated up, it kind of holds on to it for a while, right? We'll talk about that here in a second. And so when we want to talk about the amount of heat energy transferred, metal can transfer energy way, way, way faster than water can, okay? They can both transfer equal amounts of energy if they're, equal sizes and things like that and equal temperatures, but one will do it faster than the other. All right, so let's look at this term. This term is called specific heat capacity, and this is a property of any material, basically, right? So if this is the amount of energy that's needed to raise 1 gram of a substance 1 degree Celsius, okay, or 1 Kelvin, and our units are joules per gram degree Celsius. The degree Celsius is on the bottom here, or joules per gram Kelvin. Now, basically, the idea is, if I'm putting a certain amount of energy into this and it raises 1 degree, how much energy did I do to raise that 1 degree? All right. And so for water, for instance, we have a value of, about 4 joules per gram degree Celsius. Okay. And so you can kind of get the idea here, and that's actually about what we consider 1 calorie. that you get a certain amount of energy that it's going to take to raise a certain substance 1 degree Celsius. And I'll show you a table here in a little bit that shows you the comparison between all of them. All right, so specific heat is an intensive physical property. This is another property that doesn't change with the amount of matter that you have, right? So if I have a little bit of iron or I have a lot of iron, they're going to have the same specific heat capacity. They're going to have the same ability to transfer energy based upon the amount of material they have is not really a thing, right? So, you know, if I have, and again, it's because it's divided, it's per gram, right? And so whatever I have, it's always a divided value. It's a per gram. So I just have to figure out how many grams I have, and it's always going to have the same value. So it's kind of like density, where it was a grams per mil, right? And it's always a per mil. It's like a ratio. Well, this is also a ratio that per gram degree Celsius is going to make this an intensive property. So if something has a low specific heat, it's going to take a little bit of energy to raise the temperature, to get those particles moving faster. Metals are great at conducting electricity, so that means they have low specific heats, right? They heat up and cool down very easily. A high specific heat substance, like water, which has a high specific heat, takes a lot of energy to get it to raise up 1 degree Celsius, all right? But once it gets it, then it holds on to it a little bit better. Insulators have high specific heats, and so the idea here is that they don't heat up or cool down very easily. So look at some of these substances. These are some of their specific heats. You can see, you know, aluminum, which we make our aluminum cans out of for our Coke cans and, you know, things like that, 0.897, right? So that's got a pretty low specific heat. It is able to transfer energy quickly, so it can cool down that beverage pretty quickly. If you look at water here on the right-hand column, you can see it's 4.18, right? So that is much higher compared to all the other substances in this list, right? Now, again, these are all metals. There's a couple of little non-metals there. Silicon is a metalloid. Neon is a non-metal. So again, you can see something that might be a non-metal, might have a higher specific heat than a metal. Carbon, though, if you look at graphite there, it's still pretty low, right? In fact, carbon actually has a lower specific heat than aluminum does. So it actually does a better job of transferring energy than aluminum does. If you look at the one that does the best out here, wow, you can look at some pretty low ones. If I look at gold and lead, those are able to transfer energy really easily comparatively. So if you made a gold can or a lead can that you were drinking and making your soda out of, that would cool the beverage down even faster if you put it in the refrigerator than the aluminum can would. Don't recommend the lead one. All right, so this is the equation that you need to know how to use as you're getting going in you know, the worksheets and stuff that we're going to have you do. Q equals MC delta T is the way I like to say it, just because that's the way I memorized it back in the day. Here we've got Cm delta T. The C stands for the specific heat of the substance. Now remember, every substance is going to have a different specific heat. So you have to get that value from a table like the one that you saw here, right? So grab that value when you're solving these types of equations. And the one you're going to use the most is going to be water, right? You're going to probably use that one a lot because we deal with the temperature of water as we do some of the labs later on. M stands for the mass. Delta T is a change in temperature. Remember that triangle means change in, so it's a change in overall temperature. TF minus TI, the final temperature minus the initial temperature. And that gives us Q. That gives us the amount of heat transferred in joules. Now, don't forget that joules is something that you guys learned back when you were taking physical science. And it's like a kilogram meter per second squared is a Newton. And then you multiply, you take that, that's that force, right? And you force times distance is equal to work, and work is measured in joules, right? So it's like a kilogram meter squared per second squared is what we're dealing with when we deal with joules. It's been a little while, right, since physical science. But you have a bunch of other units that are kind of packed in there. And so, yeah, it's kind of fun to think about units. I like units anyway. All right, so our specific heat example, let's see how we would do a problem like this. We would ask something like this. How much heat is needed to warm 250 grams of water, which is about a cup, from 22 degrees Celsius, about room temperature, to 98 degrees Celsius, near its boiling point. Here in Colorado, it would be above its boiling point. All right, so we're obviously at a lower elevation than we are here in Colorado. And then, of course, we have the specific heat of water is listed as 4.18 joules per gram degree Celsius. All right, so let's just list our values that we know, right? So our givens, C is 4.18 joules per gram Kelvin or gram degree Celsius, either way you want to look at that. We have Celsius here and we have Kelvin. You'll notice we have Celsius in the actual problem, but we use the unit for C as Kelvin. It doesn't matter. Why? Because remember, 1 degree Celsius is equal to 1 Kelvin. They don't start at the same place, but they're equivalent to each other. They're exactly equal to each other in terms of how big each degree is. So you can throw in, you can do the calculation for C, and you can automatically assume it's the same for Kelvin, right? So 76 degrees Celsius is 76 Kelvin. So we did our little TF minus TI. And then we're solving for Q, and of course we have our mass of 250 grams. So Q equals Cm delta T. Plug those in. Don't forget to have your units as you plug them in. And again, this is important to recognize that your grams here for 250 needs to cancel out with the 4.18 joules per gram Kelvin, right? So make sure that you have the same units here. Sometimes we give you kilograms and the term on the right. We might give you the mass in kilograms. Make sure you convert that to grams first, okay? So here we have an answer of 7.9 times 10 to the 4th joules. So let's see how you would do. Here's your problem. A 2.50 kilograms, I said sometimes we give you kilograms, here it is. Piece of copper metal is heated from 25 degrees Celsius to 225 degrees Celsius. How much heat in kilograms is absorbed by the copper? Now, are you using water-specific heat here? Right? Don't forget that this is copper. This is not water. So you don't want to use that 4.18 value for specific heat. You want to use the specific heat of copper, which is 0.384 joules per gram degree Celsius. Now, if we didn't give that to you, you'd have to look it up in a table. But there it is. You don't have to look it up in a table. All right. So I want you to pause and practice and see what you get. And pause it. And welcome back. Here we go. Let's see how you did. Did you write out your givens? Right? You put down all your givens. Or I didn't show you that anyway. Well, you would put all your givens. Obviously, I did not in the PowerPoint. Shame on me. Forgot that I didn't. So if we go all the way to the step and we skip the first few steps, and we don't show all of our gems, then we have 0.384 joules per gram degree Celsius times 2,500 grams. Remember, we have to convert that kilograms to grams, and then 200 degrees Celsius is the difference. And so we'd have 192,000 joules. Now, you might be like, well, how many significant figures am I supposed to have here? Well, look at your temperature, and your temperature has the ones place in common, okay? So if you look and you're looking at 200 degrees Celsius as your temperature, you're like, what, that's only one sig fig? No. Remember, we actually measured all the way to the ones place because we measured to the 25 degrees Celsius. That's the 5 is the ones place. And the 225 degrees Celsius, and that's the ones place. And remember, when you're doing addition and subtraction, and here we're subtracting, that you line up everything according to the decimal point, right? And so here we actually can say that that 200, that last 0 in the ones place, that was actually measured. So we have 3 sig figs there. And you'll notice in the kilogram piece, we had 2.50. That's 3 sig figs. And then, of course, our specific heat also has 3 sig figs. So our final answer can be expressed in 3 sig figs. So you can write 1.92 times 10 to the 5th, or you could just convert this to 192 kilojoules, or you can leave it 192,000 joules because that's still going to be... Oh, sorry. No, you can't leave it that way because it says in kilojoules here. They actually want the answer in kilojoules. That would be a tricky one, right? If you didn't see that, you might put your answer in joules and you might miss a point there because it actually asks for it in kilojoules. All right. So let's look at this one. It says a 4.0 gram sample of glass was heated from 274 Kelvin to 314 Kelvin and was found to absorb 32 joules of heat. Okay, so now we're giving you the Q. Notice that 32 joules of heat is the Q value because it's expressed in joules. Now you're going to have to figure out the specific heat. So now you're solving for C. All right. So what's the specific heat of glass? All right. I'll let you pause and practice this, and I'll say you do. And welcome back. All right, so we plug. Okay, now I'm showing my work, right? Here's our givens, right? M is 4.0 grams. Temperature change is 40 Kelvin. And notice I put the period after there so you know, hey, that 0 is significant. It was measured to the ones place. And then 32 joules. And then I got to calculate C. So here's my original formula. Now let me rearrange my formula to calculate for C. And then I plug it in with my units, and now I get my answer of 0.20 joules per gram Kelvin. All right, so that's how you do that one. Hopefully you guys got that one. All right, so let's see. One last little bit of thing we want to talk about, and that is what calorimetry is. So calorimetry is basically the study of this heat energy that's transferred from one object to the next, and we can actually figure out like calories from the study of calorimetry, right? So a calorimeter, which is what you're looking at over on the right, and there's a few different types of calorimeters, but really this styrofoam cup one is one of the best ones that you can do. It's better than just buying a fairly cheap one that you would use for a lab. It actually works a lot better to use styrofoam cups because they really insulate well. You don't want something that's going to pull energy from your system. And the ones that you buy in the from the science store and then you use for the lab, they're actually made out of metal, which is actually not very helpful. So anyway, this particular one is great. If you're doing one for a chemistry lab, like a real technical chemistry lab, and you're trying to figure out how many calories there are on something, you'd use something called a bomb calorimeter. I know it sounds cool, right? And that bomb calorimeter kind of has the same concept, but it's a little bit more complex. It's pretty cool. Anyway, so the calorimeter is going to measure the heat that's absorbed or released, okay, and the heat energy absorbed or released, or the energy absorbed in a chemical or a physical change. And in this case, it's just a physical change. We probably have, something inside like ice, and maybe we were melting some ice to see how much energy was being absorbed by the ice, right? And so we would see that the temperature of the water would drop. And then we could look at how much, because that temperature dropped so many degrees, we could look at the specific heat of water, and we could figure out how many joules of energy there were in that, right? All right, so energy given off by the reaction is absorbed by the water, and the temperature change of the water is measured. From the temperature change of the water, it's possible to calculate the energy as heat given off by the reaction. And this is a lab that we typically do in chemistry. It's a fun one. All right, so let's see if our 16.1a, part 1, objectives have been reached. Can we distinguish between heat and temperature? Can we convert between Celsius and Kelvin temperature scales? All right, so I think that stuff is reviewed. We did that in physical science. I'm pretty sure you got that stuff figured out. Define specific heat. The amount of energy it takes to raise 1 gram of a substance 1 degree Celsius, and then to calculate the changes in energy using the specific heat equation, 2 equals mc delta T, and you just got a chance to practice that. What's calorimetry? Calorimetry is studying that transfer of heat energy in a real physical situation, and this is how you calculate calories. And we'll talk about how you would use a bomb calorimeter in another part of this unit. So, criteria for success. Can you explain the difference between heat and temperature in terms of energy? Boom, do it. Can you convert between Celsius and Kelvin and vice versa? Boom, yeah, you can. Given the specific heats of 2 substances, you can determine which will change temperature more quickly. All right, specific heat of aluminum, specific heat of copper. Which one's going to heat up faster? Copper. Why? Because it has a lower specific heat. All right, which one's going to change temperature faster? Copper. All right, which one's going to cool down faster? Copper. Right, the lower specific heat is going to make that heat up and cool down faster and transfer energy faster. Can you get any 3 variables and solve for the 3rd/4th variable? So remember, C you'll pull from a table, M you'll get, and delta T you'll get. You have to solve for Q, right? So you're given 3, you got to solve for Q. Q's the 4th. I don't know why I had the 3rd there. Anyway, hope you guys had a good time learning this, and hope it was helpful to you, and hope you have an awesome day. God bless you. We'll see you.